This is CPM Calculus Chapter 3, number 47. After completing the ramp lab in Chapter 2, Marquita decided to ride her bicycle down a nearby hill to gain more data on rolling objects. The data she collected is shown right here. So here's the data. Okay. A. Can Marquita use this table to determine her exact velocity at t is equal to 6? Well, let's look at what this table is. This table is time and distance. Okay, so let's do a quick sketch. Okay, we have time at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 to 3.1. So 3.1 is around there. 6, so 1, 2, 3, 4, 5, 6. Let's just put them all in. 4, 5, 6, 7, 8, 9. Okay, and then we have these 0, 3.8 up to almost 70. So I'm going to make these marks 10 each, 10, 20, 30, 40, 50, 60, 70. Okay, so 70, 60, 50, 40, 30, 20, 10. Okay, at time 0, her distance is 0 meters. So let me put D is in meters and T is in seconds. At time 2, her distance is 3.8. So 2 we have is something around here. At time 3.1, her distance is 9.1. So around here. At time 6, her distance is 32. So 6 we have some point around right here, right? 7.5, 49.7. 7.5, 49.7. And 9.0, 69.5. 9.0, 69.5. Okay, so her data follows something like this curve that I'm trying to sketch, right? That's her distance versus time little sketch, okay? So can she use this table to determine her velocity at t is equal to 6? So where is t equal to 6? Right here. So can we get the exact velocity? Well, we know since this is distance and this is time, the velocity is just the slope, right? Can we get this exact slope function right here? Okay, at t is equal to 6. So we can approximate it, but can we get the exact? No. So we cannot get the exact velocity with just the table of data, with just this table of data, right? We know that the function here is kind of like a parabola, right? We know that it's going to have some parabolic equation, but we don't know exactly what it is. Like, we don't know what the equation is. In part C, we could see that they're going to give us an equation, so maybe we can use that. But without the equation, we just have approximations and guesses, okay? Well, not guesses, but we can approximate it using, like, educated guesses, okay? So that's part A. No, we cannot get the exact value with just the table of data. Part B. Part B says approximate it. Well, we can do that, right? Using Hannah's method. Well, remember Hannah's method, she looked at time 4 to approximate the velocity at time 4. She used time 4 and time 5. So here we're looking for time 6, right? So let's use time 6 and time 7.5, the one right after it. So we can approximate her velocity at t is equal to 6. So v at 6 seconds is approximately, we can just say f at 7.5 minus f at 6 divided by 7.5 minus 6. Okay, well, what is the function at 7.5? It's 49.7. What is it at 6? It's 32.7. And 7.5 minus 6 is 1.5. So let's bring out our calculator. Let's plug this in. 49.7 minus 32.7, what's that? It's 17 divided by 1.5. So we get her approximate velocity is 11.33. And what are the units? Well, we know this is meters and this is seconds, so it's meters per second. Okay? So that's how we approximate her velocity. Now we're given an equation in part C. In part C, we're told that the teacher observed that the data fits the function d of t, so her distance with input of time is equal to 0.789 t squared plus 0.703 t minus 0.338. So assuming that this is the correct equation, compute the exact velocity at t is equal to 6 and t is equal to 10. So let's go ahead and do this. Well, we know that the exact velocity can be found by looking at the derivative, well, right? V of t, the exact velocity, is the same thing as if we take this equation, right, of this graph, and we find the slope function. So we know that the slope function is going to be, we write it like this, d prime of t, right? The slope function is going to be, well, we drop down the power using the power rule. It's going to be 2 times 0.789 times t plus, right, t to the 1 power plus 0.703 because we drop down the 1, and it's t to the 0 plus 0. Let's simplify that. What's 2 times that? Let's bring out our calculator. 2 times 0.789 is 1.578. 1.578 t. We don't need to write to the first power. 0.703. We don't need to write t to the 0. We know is 1, right? So we don't need to write that. Okay. So here is our exact velocity given our derivative or the slope function of our distance. Okay, so we want to know it at t is equal to 6 and t is equal to 10. So we plug in at t is equal to 6, we just plug in 6 in the input, and that's equal to 1.578 times 6 plus 0.703, right? And at t is equal to 10, we just have the velocity with input of 10, and that's 1.578 times 10 plus 0.703. Let's plug these both in our calculator. 1.578 times 6 plus 0.703, and we get 10.171. Okay, 10.171. We plug in this one here. So let's just change this. We know it's going to be 1.578 times 10 plus 0.703. We get 16.483. 16.483. Okay? Put our calculators. So then we know at times equal to 6 seconds, the velocity is 10.171. And what are the units? Meters per second. Okay? So remember, this is time is equal to 6 seconds. This is the speed, and time is equal to 10 seconds. The velocity is 16.483 meters per second. Okay? Alright, well, Hannah's method in part B showed us that it's approximately 11.33 meters per second, and 10.171 is not that close, but it's relatively close. It's not like 100 or some large factor off. It's just like one or so meters per second off. And at 10 seconds, she's just going a little faster. Okay? And this ends CPM Calculus Chapter 3, number 47.